Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here is the essay. The development of quantum electrodynamics represented a monumental achievement in 20th century physics, uniting quantum mechanics and electromagnetism into a single, predictive framework. Julian Schwinger's contributions, culminating in his 1954 work, solidified this unification and provided powerful tools for understanding the behavior of light and matter at the quantum level. This essay undertakes a careful evaluation of the claims and arguments presented within Schwinger's treatise, examining its structure, methodology, and overall impact on the field. We will navigate its complex terrain, providing a granular assessment of its specific sections and demonstrating its intellectual significance. Section 1: Introduction to Renormalization and the Schwinger Approach. Schwinger's quantum electrodynamics addresses the challenges posed by infinities arising in perturbative calculations. These infinities, a significant obstacle in earlier quantum field theories, threatened to render the entire framework useless. Schwinger's approach, detailed in his 1954 publication, centers on the process of renormalization. This involves systematically absorbing the infinite quantities into a redefinition of physical parameters, such as the mass and charge of the electron. This strategy allows for the extraction of finite, physically meaningful predictions from the theory. The initial sections of Schwinger's work meticulously lay out the conceptual and mathematical framework for this renormalization procedure. It establishes a clear distinction between bare parameters, which appear in the fundamental equations, and renormalized parameters, which are directly observable in experiments. Evaluation of this section reveals a sophisticated and rigorous approach to handling these divergences, demonstrating Schwinger's profound understanding of the underlying physics. He presents an organized, unambiguous strategy for how these troublesome quantities can be surgically excised from the equations, leaving behind a healthy, predictive theory. The manner in which he frames this removal as not merely a mathematical trick but as a fundamental reflection of how we should understand physical constants demonstrates a novel Section 2: The Schwinger-Dyson equations and their application. A cornerstone of Schwinger's QED is the set of integral equations known as the Schwinger-Dyson equations. These equations provide a non-perturbative approach to solving the theory, offering a way to calculate the Green's functions, or propagators, for the electron and photon. The initial derivation of these equations, a meticulous process involving the manipulation of quantum field operators and functional derivatives, forms a significant portion of the work. Schwinger's exposition demonstrates the deep connection between the dynamics of the quantum fields and the correlation functions that describe their behavior. He carefully spells out the relationships between various Green's functions, connecting them to fundamental physical quantities. The claims in this section suggest the possibility of solving QED beyond perturbation theory. However, the complexity of the equations makes finding exact solutions exceedingly difficult. Approximations and truncations are generally required. Upon evaluation, Schwinger-Dyson equations are seen as a powerful conceptual tool, providing insight into the non-perturbative structure of QED, despite their practical limitations in providing explicit solutions, which Schwinger acknowledges, pointing toward future areas of research. The rigor in his derivation of these equations showcases his command of functional methods. Section 3: Vacuum polarization and the Lamb shift. Schwinger dedicates a significant portion of his work to exploring the phenomenon of vacuum polarization. This arises from the creation and annihilation of virtual electron-positron pairs, which effectively screen the electric charge of a bare electron. He provides a detailed calculation of the vacuum polarization tensor, a mathematical object that describes how the effective charge seen by a test charge varies with distance. The results are then applied to the calculation of the Lamb shift. The Lamb shift, a tiny energy difference between the two energy levels of the hydrogen atom, provided early experimental evidence for the validity of quantum electrodynamics. Schwinger claims that his theoretical calculations, based on renormalization and vacuum polarization, accurately reproduce the observed Lamb shift. Examination of this section highlights the impressive predictive power of the theory. Schwinger meticulously details each step in the calculation, demonstrating the strength of his methods. The correct prediction of the Lamb shift, a triumph of theoretical physics, solidifies the validity of quantum electrodynamics and Schwinger's contributions in particular. Its success provided significant validation, confirming the importance of vacuum polarization in understanding atomic structure. Section 4. Anomalous magnetic moment of the electron. Another key achievement presented in Schwinger's QED is the calculation of the anomalous magnetic moment of the electron. This quantity measures the deviation of the electron's magnetic moment from its classical value, a purely quantum mechanical effect arising from its interaction with virtual photons. Schwinger's calculation, a tour de force of perturbative quantum field theory, famously predicted that the anomalous magnetic moment is approximately equal to alpha divided by 2 pi, where alpha is the fine structure constant. This prediction agreed remarkably well with experimental measurements. Schwinger elucidates the intricate Feynman diagrams that contribute to this effect, carefully evaluating each term in the perturbation series. He demonstrates the delicate balance between different contributions, highlighting the accuracy needed to obtain a precise result. Evaluation reveals this work as a landmark calculation, showcasing the power and precision of renormalized quantum electrodynamics. The agreement between theory and experiment provided compelling evidence for the correctness of Schwinger's approach. His masterful computation of the anomalous magnetic moment remains a celebrated result, even with modern, more precise calculations, still being remembered for its elegance and accuracy. Section 5. External field problems, scattering and radiation. The sections addressing external fields deal with the application of QED to situations where electrons interact with macroscopic electromagnetic fields, such as those created by lasers or particle accelerators. Schwinger explores the processes of scattering and radiation in the presence of these external fields. He develops a formalism for calculating scattering amplitudes and radiation rates, taking into account the effects of renormalization. Schwinger argues that his methods provide a consistent and reliable way to analyze these phenomena. He demonstrates how the interaction with an external field can lead to the emission of photons and the deflection of electron trajectories. Upon evaluation, the strength of this area lies in its generality and applicability to a wide range of experimental situations. Schwinger's formalism provides a versatile tool for analyzing diverse phenomena, from electron scattering in solids to the behavior of particles in high-energy colliders. His treatment of external fields contributes to the versatility of QED as a framework to model particle behavior under electromagnetic influence. Section 6. The mass renormalization program in detail. Schwinger provides a detailed discussion of the mass renormalization procedure, describing how the infinite mass of the bare electron is absorbed into a redefinition of the physical mass. He presents various regularization schemes, such as Pauli-Viller's regularization, which are designed to make the intermediate calculations finite. The process involves introducing fictitious particles with large masses and carefully chosen couplings, allowing for a controlled way to handle the divergences. Eventually, the regulator masses are taken to infinity, leaving behind a finite result for physical quantities. Schwinger claims that the physical mass of the electron is a measurable quantity, independent of the regularization scheme used in the calculation. Evaluation shows the sophistication of the renormalization method. The careful handling of infinities is crucial for obtaining finite and meaningful predictions from the theory. Schwinger's meticulous treatment reveals the deeper connections between the bare parameters in the Lagrangian and the physical quantities experimentally observable. His emphasis on the independence of physical results from a choice of regulator demonstrates the consistency of the renormalization program. Section 7. Charge renormalization. and the fine structure constant, Schwinger dedicates a substantial portion to the discussion of charge renormalization, in which the infinite charge of the bare electron gets absorbed into a finite physical value. This involves considering the effects of vacuum polarization, where the presence of virtual electron-positron pairs screens the bare charge. He explains how the physical charge, as measured in experiments, is smaller than the bare charge. Schwinger demonstrates that the renormalized charge depends on the energy scale at which it is measured. This energy dependence is related to the running of the fine structure constant. He claims that the fine structure constant, which determines the strength of electromagnetic interactions, is not truly constant, but varies slowly with energy. The exploration validates the importance of vacuum polarization in determining the observed value of the electric charge. Schwinger's deep understanding of renormalization allows him to connect the bare charge to the physically measurable charge. His emphasis on the running of the fine structure constant anticipates later developments in quantum field theory, particularly in the context of quantum dynamics. Section 8. The S-matrix and scattering cross-sections. The concept of this matrix, which encodes the probabilities for different scattering processes, lies at the heart of Schwinger's quantum electrodynamics. He carefully defines this matrix and demonstrates how it can be calculated using perturbation theory. The process involves expanding this matrix in terms of Feynman diagrams, which represent the various ways in which particles can interact. Schwinger then discusses how to relate this matrix elements to physical observables such as scattering cross-sections. These cross-sections determine the probability that particles will scatter into specific directions. He claims that the calculated scattering cross-sections agree with experimental measurements, providing further validation for his theoretical framework. His formalism lays out a robust framework for analyzing scattering phenomena. Schwinger demonstrates how this matrix can be used to predict the outcomes of experiments, reinforcing the predictive power of the theory. His meticulous calculations of scattering cross-sections provide a crucial connection between theory and experiment. Section 9. Gauge invariance and the Ward identity. Schwinger emphasizes the importance of gauge invariance, a fundamental symmetry of electromagnetism, in formulating quantum electrodynamics. He demonstrates that his theory is manifestly gauge invariant, meaning that the physical predictions are independent of the choice of gauge. This is ensured by the Ward identity, a mathematical relation that connects the vertex function, which describes the interaction between electrons and photons, to the electron propagator. Schwinger uses the Ward identity to simplify the renormalization procedure and to ensure that the theory remains consistent even when infinities are present. He argues that gauge invariance is a crucial requirement for any physically acceptable theory of electromagnetism. This section displays an advanced comprehension of the underlying theoretical structure of QED. The Ward identity ensures the consistency of the theory, even in the presence of infinities. Schwinger's meticulous adherence to gauge invariance is a hallmark of his approach to QE. Section 10. Higher-order corrections and the limits of perturbation theory. Schwinger acknowledges that perturbation theory, while powerful, has its limitations. He discusses the importance of higher-order corrections, which arise from more complicated Feynman diagrams. He notes that these higher-order corrections can be difficult to calculate and may lead to new types of infinities. Schwinger also considers the possibility that perturbation theory may break down at very high energies or very strong coupling strengths. He poses that, while QED works remarkably well at accessible energies, its validity at extremely high energies remains uncertain. The evaluation of this section indicates a balanced and nuanced perspective on the strengths and weaknesses of QED. Schwinger acknowledges the limitations of perturbation theory. He emphasizes the need for caution when applying QED to extreme conditions in which the theory begins to show signs of its own limitations. Section 11. Comparison with other approaches to QE. Schwinger, in his work, implicitly compares his approach with those of other pioneers in the field, particularly Richard Feynman and Shinichiro Tominaga. While he does not engage in direct polemics, His emphasis on field-theoretic methods and his focus on gauge invariance reflect a different philosophical approach compared to Feynman's more diagrammatic and particle-centric perspective. Schwinger's formulation, deeply rooted in the principles of quantum field theory, prioritizes the fundamental quantum fields over particle trajectories. He emphasizes the importance of maintaining gauge invariance at every step of the calculation, reflecting a commitment to the underlying symmetries of electromagnetism. The work emphasizes a more rigorous, axiomatic approach to quantum field theory. It stresses the importance of mathematical consistency and conceptual clarity. Schwinger's approach, while mathematically demanding, provides a deep understanding of the underlying structure of QE. Section 12 Contemporary Reception and Subsequent Developments. The reception of Schwinger's work was initially mixed. While his technical brilliance was widely acknowledged, his emphasis on abstract field-theoretic methods and his avoidance of intuitive diagrams made his work less accessible to some physicists, particularly those trained in the more pragmatic approach of Feynman. Over time, however, Schwinger's contributions have come to be recognized as foundational to the development of modern quantum field theory. His techniques for renormalization, his treatment of gauge invariance, and his insights into the structure of this matrix have become standard tools in the field. Subsequent developments in quantum field theory, such as the understanding of asymptotic freedom and the development of non-perturbative methods, have built upon the foundations laid by Schwinger. The initial challenges in accessibility have been overcome by its impact on the long-term trajectory of the field. Schwinger's rigorous approach has influenced both theoretical developments and experimental applications. Section 13 Evaluation of specific claims regarding divergences. A significant claim of Schwinger's work is that divergences in QED can be systematically removed through the process of renormalization, leading to finite and accurate predictions for physical observables. Examination shows this claim held true within the perturbative regime. Schwinger provided a detailed and consistent prescription for dealing with infinities, demonstrating that the physical parameters, such as the mass and charge of the electron, can be redefined to absorb these divergences. This enabled calculations of quantities like the Lamb shift and the anomalous magnetic moment of the electron, which agreed remarkably well with experimental data. While the renormalization procedure was initially viewed as a mathematical trick by some, its success in providing accurate predictions solidified its importance as a fundamental aspect of quantum field theory. His work helped to legitimize renormalization as a way to approach quantum field theories with infinities. Section 14 Conceptual Framework and Mathematical Rigor. Schwinger's conceptual framework emphasized the importance of quantum fields as the fundamental objects of reality, rather than particles. He developed a mathematically rigorous formalism for describing the interactions of these fields based on the principles of quantum mechanics, special relativity, and gauge invariance. The application of this framework resulted in insights into the structure of quantum electrodynamics. He showed how the properties of electrons and photons are interconnected through the underlying quantum fields. His conceptual framework provided a deep and consistent picture of the quantum world. A significant aspect is his deep commitment to mathematical rigor. His work provides not only a set of practical tools for calculations, but also a deep understanding of the mathematical foundations of quantum electrodynamics. Section 15 Legacy and Enduring Significance. Schwinger's legacy extends far beyond his specific calculations. His work laid the foundation for many subsequent developments in quantum field theory, including the Standard Model of particle physics, his techniques for renormalization, his treatment of gauge invariance, and his emphasis on mathematical rigor have become standard tools in the field. Schwinger's influence can be seen in the work of many leading theoretical physicists. He provided a bridge between the more abstract mathematical formulations of quantum field theory and the concrete experimental results physicists sought to explain. He demonstrated the power of theoretical physics to make accurate predictions about the behavior of the quantum world. He established a new standard. Section 16 Conclusion, a triumph of theoretical physics. In conclusion, Julian Schwinger's 1954 work on quantum electrodynamics represents a monumental achievement in theoretical physics. His careful treatment of renormalization, his masterful calculations of physical observables, and his deep conceptual insights significantly advanced our understanding of the quantum world. While the work presented challenges in accessibility and faced initial skepticism, its impact on the development of quantum field theory is undeniable. Schwinger's legacy endures as a testament to the power of theoretical physics to make accurate predictions. His contribution allows an understanding of the fundamental laws governing light and matter at the quantum level. His work solidified QED as one of the most successful theories in physics, with its predictions verified to an extraordinary degree of precision. The thorough investigation of his claims underscores its enduring significance and cements Schwinger's place as one of the giants of 20th century physics.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.